All right, good morning, you guys. Today we're taking on more with confidence intervals. You knew this day was coming. All right, so a sampling distribution describes the results of lots of samples from the same population. If you repeatedly select random samples of the same size, then the values of the sampling proportion of successes, p hat, the statistic, have this approximate normal sampling distribution. So I keep showing it to you, but here we are again. So we're picturing all of these different statistics, and when we put them all together, right? So we're picturing lots of samples from the same population on all of these different statistics that we obtain. When we put them all together, they have the shape of a normal distribution with that normal curve overlaid. So we anticipate that our true parameter, that elusive true parameter, right, the truth about the population, should be right smack in the middle, right? So in our perfect world, that's where it would fall. Okay, what is going to change here is instead of calling this right here standard deviation, right? So how far a typical value will fall from the mean. So instead of calling it standard deviation, we actually call it something else now. We call it standard error. Okay, and then this format right here, I'm just going to switch it ever so slightly. I pulled this from your textbook. It has p times its complement, which would of course be what we've been calling failure. So I'm going to rewrite this as the square root of p times q divided by n. And we're going to be building off of statistics here, so I'm going to give it the little hat on both. Okay, so we're looking at p hat times q hat divided by n, and then the square root. And our mean right here, right, that's what the true parameter is right there. We're anticipating that it's right smack in the middle. So let me just draw out that picture so you have it for your notes, right? I'm just picturing a bunch of statistics and what they look like when we have them all lumped together, right? This is what we're kind of picturing. Right, a whole slew of statistics looking roughly like so. I'm going to overlay that normal curve like that. And again, right there, right smack in the middle should be the true parameter, the truth about our population. So again, we call it standard error here instead of standard deviation because we don't know what the parameter is. We don't know what p is, and we're trying to estimate it with a certain amount of room for error. So let me add that off to the side. So we call it standard error. Instead of standard deviation, because we don't know the true parameter. And we're trying to estimate it with a certain amount of room for error. Okay, so again, a recap. We're picturing lots of samples from the same population. When we gather all of their statistics together, right, the proportion of successes, all those p hats, it has this shape of a normal distribution. Okay, we are picturing right smack in the middle. That's the true parameter, right? What we're trying to approximate, estimate, but we don't know its actual value. And then instead of calling it standard deviation now, we've changed its name. We've called it standard error, but its calculation is pretty much the same. We're looking at the statistic times its complement divided by our sample size, and then we take the square root of it. Okay, so in our last section, we knew the population proportion, the parameter. So when we started talking about sampling distributions, we knew that value. Okay, now in this section, we do not know it, right? It's that elusive value that we're trying to approximate. We're going to use the sample proportion, the statistic, to estimate it. So again, our parameter, that's the P, right? That's talking about the entire population, and our statistic is the P hat right there. So we know that parameter describes a population, statistic describes a sample. So to construct a confidence interval for P, we want to check the following assumptions. So we see that a lot of these just transfer over from what we were talking about with sampling distributions. So randomization, right? We want our data to come from a random sample from our population of interest. It should represent our population well. Okay, independence, right? Our data values should not affect each other. Okay, 10% condition. Our sample size should be less than 10% of the population. And then the success failure condition, we must expect at least 10 successes and at least 10 failures. So that is when we've been doing the NP, we're just going to call it NP hat now, has to be greater than or equal to 10. And same with NQ hat like that, must be greater than or equal to 10. And something that we learned about before is the reason that we like randomization, right? We like randomization because it minimizes any bias, right? Every individual is selected at random, so it should do a good job of representing our entire population of interest. And then the reason that we want to make sure we have at least 10 successes and 10 failures, we want to have as big of a sample size as possible to reduce variability. All right, so assuming we can meet these criteria, that means that our sampling distribution of our statistic should be approximately normal, so beautiful bell-shaped curve. The mean of the sampling distribution is the true parameter, right? That's what we're saying here. That's what we're saying here again. And then since we don't know the true population parameter, we use P hat as our guessed value of P. So that is crucial. I'm going to underline it for emphasis. Okay, so 3 formulas that we're going to get here, and I will obviously put these on your next quiz. I will give them to you. So SE, right here, right, that is standard error. Okay, so square root of P hat times Q hat over N. Okay, here, margin of error, MOE, margin of error. Okay, and then here what we're seeing is this Z with a little asterisk, and that's actually called our critical value, and we're going to talk about that more on the next page. So our critical value and then multiplied by, right, that looks familiar. That's right here. That's the standard error. Okay, and then putting it all together, our confidence interval will be our statistic with the margin of error attached to it. So that P hat, again, that is our statistic, okay, with that margin of error attached to it. So I'm going to keep that as MOE, and then just remind you again that this part was the critical value. And then this part right here is the standard error. So we were doing this back when we were talking about it with only 95% confidence, right? We had our statistic with our margin of error attached. All we're doing now is getting a little bit more specific, a little bit more technical in how we're doing our calculation. So again, just a little bit more with confidence intervals. The confidence level we set determines the percent of all possible samples that are expected to contain the true population proportion, the parameter. So when we say 95% confidence, we're saying that repeated samples from the same population produce different confidence intervals, right? Because we're getting different statistics, right? But with that margin of error attached to it, we know that in 95% of these intervals, we are capturing the true population proportion. So I've shown you this picture before, but I thought it was worthy of revisiting now because what we're looking at with these little dots, the little dot is all the statistics. So right here, what this is representing right there in the middle, right, that is our statistic with the margin of error attached to it. So we're picturing these intervals. So we have different statistics. Everywhere the little ball is, right, that's a different statistic. And then we're attaching the margin of error on both sides of it. And we're seeing that our true parameter, right, that's what this bar is, this vertical line, right? We're seeing that in most of these, in fact, all of them except for this one, captures that true parameter. So all of the confidence intervals capture that true parameter except for this one. So let me add that to our notes. So all of these confidence intervals capture the true parameter that's the P, except this one. Okay, so that would be part of that 5% of the time that we just miss. Every once in a while, we get just kind of a abnormally high or low statistic that when we attach the margin of error to it, right, it does not contain that true parameter. But in 95% of samples, when we attach our margin of error to the statistic, we are capturing the true parameter. All right, let's go to the next side. Okay, so here, again, just reminding you of our confidence interval, right? We did that structure on that other page. So just again, this right here is your statistic. We mentioned that we're going to have a critical value. And then right here is the standard error. Okay, so here, this is where our mean is, right here, right, z-score of 0. So our critical value here and here, we're seeing that it's going on either side. And it's telling us how many standard deviations we are away from our mean. So our critical value ends up being a multiplier that makes the interval wide enough to have the stated capture rate. Okay, so we're trying to capture certain levels of confidence. And we've done 95, we've done it in a basic way, and now we're going to do it a little bit more complicated. So let's look at how would we get the critical value to be 90% confident. So if we're trying to be 90% confident, let me just shade what that would be. That would be the middle 90%, right? We've been doing this skill. We're just finessing it now. We're adding a little bit more to our understanding of why we've been finding the z-scores that align to the middle 90% of data. So here, I'm just going to write here, middle 90%. So if this is the middle 90%, right, it leaves me 10% in either tail region. So when I split it two ways, I got 5% over here and 5% over here. And I'm trying to get the z-scores that go with those two markers. And I'm just calling them something different now. I'm calling it a critical value. So to get to that z-score right here, I know that I can use inverse norm. So I'm going to do inverse norm. The area below would be 0.05. Mean is 0, standard deviation of 1. So when I plug that into my calculator, I should get a z-score of negative 1.64. Let me just remind you of how I'm doing that. So I'm hitting second vars, and I'm going down to inverse norm, 0.0501. So it's getting me, I'm going to go 2 decimal spots for all the critical values. I'm going to be really consistent with that. So I get negative 1.64. So Z would be about negative 1.64. So that's what it would be here. Here would be its positive counterpart, right? They have the same magnitude, the same distance from the mean. So we'll see the positive and negative. And then when we write it as a critical value, we use Z with a little asterisk like that. And we say that it's about 1.64. So let's just write it as a positive because it's a multiplier and it will go in either direction anyways. So we'll see that in just a moment. So the critical value, that little Z star or Z asterisk, it's about 1.64. And I'm saying round all critical values to the nearest hundredth. Okay, so these next two are super similar. Now we're just looking at 95% confidence. So we're thinking middle 95%. So let me shade what that looks like to me. So maybe about here to here. So middle 95%. So that leaves me with 5% that I'm going to split 2 ways. So 2.5% here and 2.5% here. So my area below here would be 0.025. So I'm going to use my inverse norm, 0.025 and then 0.1. And that's going to give me a z-score of about negative 1.96. So right here would be the negative 1.96. Here would be its positive counterpart. So when I write it as a critical value, z little asterisk, it would be 1.96. Okay, 99% confidence. Okay, that's most of it, right? So I'm here to about here. So middle 99%. Let me write that. So middle 99% leaves me with 1% that I need to split 2 ways. So that would give me 0.05%, or not 0.05%, 0.5%, 0.5%, and then 0.5% there, right? Because I'm just splitting the 1% 2 ways. So 0.5% in each of those tail regions. So as a decimal, that would be 0.005. So I need to do inverse norm, 0.005. 0.1. And that's going to pump out a z-score of about negative 2.58. So I have z is about negative 2.58 here and positive 2.58 here. So my critical value will be about 2.58. All right, so hopefully we are pretty set on how we get to the critical value. It is the same skill that we've been doing for a while, right? When I say find the z-scores that correspond to the middle, 70%, 80%. Now we're just looking at the 90, 95, and 99, since those are the most common confidence levels that we see. We know that 95 is the one that we see most often when we're reading a newspaper or watching them discuss political polling, for example, on the news. Okay, so these are the critical values that go with those most common confidence levels. All right, let's flip it to the last sheet. Okay, so here in 2015, Gallup sampled 1,009 U.S. adults. So that's crucial because that's telling us the end value, our sample size. 616 reported actively trying to avoid drinking soda. Show that the conditions for calculating a confidence interval for a proportion are satisfied. Okay, so first we're looking at randomization. So do we have randomization? Okay, doesn't always say it explicitly, right? Sometimes it says random, sometimes it says SRS, sometimes it cites a reputable organization. So since they're talking about Gallup, we trust Gallup. Gallup uses randomization. So I'm going to say, yes, we have fulfilled that criteria. Okay, independence. Do we assume that if it's, taken at random, then one outcome doesn't influence the next? Then yeah, we're saying, yeah, it looks like we have independence. Okay, 10%. So does it look like, the 1,009 U.S. adults is less than 10% of all U.S. adults? Absolutely. So we're fulfilling that 10% criteria also. Okay, and then success failure, I actually have to solve for. So let me just write success failure and then show the math to back that up. I need at least 10 successes, at least 10 failures. So I'm looking at, is n times p hat greater than or equal to 10? How about n times q hat? So here, if I define what n is 1,009, right? It's my sample size. P hat would be the 616 out of 1,009. I'm just going to leave it as a fraction right now. And then Q hat would be its complement. So those that are not actively trying to avoid drinking soda. And that would be the 393 out of 1,009. Okay, so if I just check it, right, I'm going to see that I definitely have well more than 10 in each group. So I'm just showing the 1,009, and when I multiplied that by 616 over 1,009, right, it's telling me, well, you got 616 successes, right? 616 individuals who are actively trying to avoid soda. We're well above 10. Okay, over here, if I just verify it, I have 1,009 for my sample size. And then 393 over 1,009 will leave me with 393. So we definitely have well more than 10 that are not actively trying to avoid drinking soda. So we know that the idea here is just finding that sweet spot. We want it to be big enough, but not too big. So we definitely have shown that we've met all 4 conditions. All right, so now we need to find our 95% confidence interval for the proportion of all U.S. adults who are actively trying to avoid drinking soda. So first we need to find the critical value. So find that critical value. So here, remember 95% confidence. So we're thinking, well, what would be the area that would correspond with that? So if I picture it, we did it on that other sheet, but just to remind you, right, here's that middle 95%, and I'm looking for these markers. So that 5% is being split 2 ways. So 0.025, let me just write it as 2.5%, since everything's in a percent here. So the area below here would be 0.025. And I want to find the z-score that goes with it. So inverse norm, 0.02501. Okay, and some of you may have noticed that your calculator already defaults to the mean being 0, standard deviation of 1. So you can actually just type that part in and it goes a whole lot faster. So here I'm going to get, in my calculator, when I type this in, it's going to give me the negative. Let me show you. So inverse norm, 0.025, is going to give me z is negative 1.96. But when I think of it as a critical value, I'm just marking it as the positive. So z, little asterisk, 1.96. Okay, so I found my critical value, I found my multiplier. So now, here I need to figure out, well, what's my confidence interval? So I'm looking at my statistic with the margin of error attached to it. And my margin of error is that critical value, right? That's my multiplier on my standard error, square root of p hat times q hat over n. Okay, so my statistic that I'm building off of is the 616 over 1009, plus or minus. My critical value is 1.96. Okay, and then my standard error, let's plug in. So I'm plugging in 616 over 1009 times 393 over 1009, and then I'm dividing that by, well, 1009. Okay, so let me go ahead and crunch that. So when I'm looking at my standard error first, I'm taking 616 divided by 1009. Let me show you. Okay, times 393 divided by 1009. Dividing that by 1009. And then I'm taking the square root. Okay, so right there is my standard error. And then I have to multiply that by 1.96. So right there is my margin of error. So right here, this whole part as a decimal was 0.0301. 616 divided by 1009 is 0.6105. Okay, so what I have here is my statistic. Here is my margin of error. So you could leave your answer like that. You could actually attach it, right? So I could leave it as statistic with that margin of error attached, or if I take 0.6105, subtract 0.0301, and then add 0.0301, it can build me that window as well. So I could also write it as 0.5804 to 0.6406, and I could write that as a percent as well. So 58.04% to 64.06%. All of these ways are perfectly acceptable for your answer. And again, what this is telling us is that we are 95% confident that the true parameter falls within this window. Okay, and then I wanted to do it with you just one more time to really drill it in. So here in example 3, first part, check the criteria. I'm just going to talk you through A, and I'll just do it a little bit more quickly. So here, let me just read this out. 2012, Gallup sampled 1,018 U.S. adults, found that 31% believe that gambling is morally wrong. So if I check my criteria, randomization, yeah, we trust Gallup. Independent, yeah, we have no reason to believe that one outcome would influence another, so we're assuming that we have independence. 10%, well, again, if we're looking at 1,018 U.S. adults and we have about 327 million people in the United States, I'd say that we're well below 10% of our total population. Success failure, so if I multiply my 1,018 adults by 0.31, I would definitely be well above my 10 successes. So I have 315 successes and change. N times Q hat. So if I take my 1,018 and I multiply by the 69% who do not think gambling is morally wrong, I now have about 702. So again, all my criteria are met. I just need randomization, independence, 10%, and success failure. That's what I'm checking here. So we're all good. Let's push ahead to part B. So here, find a 92% confidence interval for the proportion of all U.S. adults who believe that gambling is morally wrong. So step 1, we need that critical value. So if I visualize it, again, I can picture middle 92%, right? That's what I'm picturing right here. That leaves me with 8% left, and I split it 2 ways. So I have a 4% here and a 4% here. So I'm picturing what those z-scores would be, and then I'm just making my critical value, whatever the positive would be. So here I need to do inverse norm, 0.0401, and that's going to pump out a z-score of negative 1.75. So my critical value then will be positive 1.75. Okay, so then my confidence interval, right, almost done here. So confidence interval, again, it's p hat plus or minus critical value times the standard error. Okay, so my statistic is 0.31, right? 31% who believe gambling is morally wrong. My critical value, just solve for it, 1.75. Okay, my standard error, so 0.31 times 0.69 divided by 1018. Okay, so when I plug all that in, I'm going to end up here with a margin of error. So 0.31 plus or minus margin of error will be 0.0254. So that is my statistic. This is my margin of error. If I actually attach the margin of error, so if I calculate 0.31 minus 0.0254 and then I add it, it builds me a window. So 0.2846 to 0.3354, or 28.46% to 33.54%. Okay, so again, we would be now 92% confident that the true parameter falls within this window. Okay, so now if I just write out what my confidence statement would say, something like, we'd say, well, according to Gallup, so according to this source, this is what we found. That's how we start. So according to Gallup, or according to the poll, we know that 31% of the U.S. adults that were sampled think gambling is morally wrong. Okay, so first part, concretely, this is what I know. Okay, building off of that, we're saying, well, we are 92% confident that the true parameter, or the truth about the population, is going to be within, okay, I'm just going to write that number here as a percent, since I wrote it as a percent here, 2.54%, okay, plus or minus 2.54% of this result. Okay, I could also build the window and say, oh, well, it should fall within 28.46 to 33.54%, right? So I could either say, this is my statistic, this is my margin of error, like I'm doing here, or I could attach it and build the window. Either way is fine. Okay, and then what is that really telling me? It's telling me that in 92% of samples, right, so same sample size, same methodology, that true parameter, that elusive true parameter, should be within that window that we've created. So our statistic plus or minus the margin of error. So we would expect our true parameter to fall within that window 92% of the time. Okay, we know that 8% of the time, it is not going to. And again, we never have any guarantees. We're just trying to make estimations, predictions about a larger population based on a representative sample. All right, I hope you guys are doing well. Have a wonderful rest of your day.